this video is only for enrichment and is optional and is public for anyone to see that might be able to, see this on my YouTube channel. It is absolutely not expected. I don't know, the county's not sure yet what they're going to do. An instruction, you should be on break and thinking about your health of you and your family and your loved ones. And again, this is just here as a resource if you want it, to continue to enrich the instruction that we had before before we were sent on break. So again, this is just optional to enjoy or to practice. So this warm-up would have, this warm-up I have is stuff that we've already learned how to do. And this is building a power series from scratch. And again, really the only way we know how to do that right now is if we recognize something that's geometric, right? So I look at this function and I say, ha, I see you a over 1 minus r, right? My a is 6 and my r is x. Excuse me. So I can build a power series, and it wants the first 6 terms. So since I'm not writing an infinite series, this is only going to be approximate, right? And it's going to be a r to the 0 plus a r to the first plus a r to the second, and so on and so forth. Where am I? Lost track of how many? I got 3 so far, right? So let's count. Do I have 1, 2, 3, 4, 5, 6? So the first 6 terms of the power series. And as you remember, perhaps, again, this is all because I recognized my geometric series with an infinite sum of a over 1 minus r. Notice the next question is asking you to evaluate the actual function x0. Well, that's easy. 6 over 1 minus 0, which is 6. And then the polynomial, right? This is the 6-term polynomial that we just got. So to evaluate that, I have to plug in. Now remember, this term right here is 6. Maybe I should write out this, right? This is 6 plus 6x and I think you can see what happens when I put 0 in there, right? All of these terms, when I put in 0 for x, that's all going to go away. And what am I going to get? I'm going to get 6 as well. And remember, we talked about the idea of the center of a polynomial expansion. The center, right? There's no shift on x. So this center of the polynomial expansion was x equals 0 because there was no O shift. So the polynomial and the function are equal at the center. When x was equal to 0, the polynomial was equal to the function. And remember, I showed you before we left about how as you radiated to the right and left of the center, the polynomial, not the infinite one, but the truncated or cut off polynomial, was close to the function but had some error. So these problems in your textbook you do not have to do because there is no assignment. There is no assignment, there's no expectation. This stuff will not be checked and you will not be assessed on this now or when you get back. It is just for your enrichment. That the solution to these problems, if you want to look at how these kinds of problems are done, you could practice them for enrichment, you could check the solutions, but there is no assignment. So, reflecting on some big ideas of previous instruction, we said that the polynomial, the function equals, right? The function equals its infinite polynomial on the interval of convergence, right? And I didn't talk about it in the warm-up, but in the warm-up, right, I didn't ask for the interval of convergence, but remember the interval of convergence comes from the geometric series where the absolute value of your r needs to be less than 1, strictly less than 1. And for us, that would mean, to put an interval notation, that x needs to be between -1 and 1, and I would get that many converging power series. But, oh, that's my kids playing lacrosse and hitting my house. The function is only approximate, is approximated by the truncated polynomial. Right? That means cut off, truncated, cut off. With n terms, for instance, like our warm-up had 6 terms, and within the interval of convergence. And the approximation gets better and better as the number of terms approaches infinity. The function is equal to the truncated polynomial, strictly equal to, but only at the point of tangency, or the center. So what we did in the warm-up was given, what, hon? Huh? What you need? Are you recording? Yeah. Oh, sorry. That's okay. What do you need? No, I just want you to come look where we start, that's all. Look at what? The stuff I did. Oh, okay. Hold on, kids. Keep recording. All right. So given a function, we can, and we did, get out and construct from scratch. I told you can think of that, the analogy is a baker, right? A baker with all the ingredients. No box cake, no box brownies. You're at the flour, the baking powder, the salt, the sugar, the whatever, and you're building a power series from scratch. But our ability to do that was based on the fact that we saw the geometric series pattern, right? What if that doesn't happen? What if we have to, what if that's not the only series that I want to be able to build from scratch? So, that's what we know so far. I wonder what else could be out there. Now, to be a power series, you do have to be in this form where you've got coefficients, right? Coefficients here, and then you have x, or x with a shift to integer powers, right? Increasing. Right? There's the other form, and that's only when you've got a shift of x off of 0. Right? But that is a power series. To be called a power series, you have to be in that form. Our coefficients are constants. The center A is also a constant. Remember, up here, I do have a center up here. Right? My center is just 0. And we talked about this on Friday. The first series would be centered at the origin if you graphed it, and the second series would be shifted right or left. A is being your new center, and then your error would increase as you moved right or left from the center. So that's, again, recap. I got the power. Building a power series from scratch. Only, caveat, fine print, if you recognize a geometric series. A over 1 minus r. So, what about when I have a function that isn't geometric? I don't have an a and I don't have an r. Now remember, I showed you on Friday that sometimes I can take a derivative or an antiderivative of a given function and generate an a over 1 minus r. But what if that doesn't work either? So just watch this. There is an infinite polynomial. I want to solve for the, because after all, I can write x to the 0, x to the 1, x to the 2, x to the 3, but how do I find those freaking coefficients? So the first thing I did was plug in 0. And if I plugged in 0, now you do have to think about x to the 0 being evaluated first, right over here. X to the 0 is 1. We think about that first before we think about plugging in 0. So when I plug in 0, all these other terms go away, right? I plug in 0, that term goes away, that term goes away, and all the rest of them with x go away, and I'm only left with that first coefficient. Then I went back to the original polynomial and I took a derivative. The first term went away, right? And then I went up here, brought the 1 down, and this is now x to the 0, which of course is just a 1, so that's where the c1 comes from. Then I plugged in 0 to the derivative, and shocker, look what happened. I think I see a pattern here, right? If I just take derivatives and then plug in the center, I get the coefficient. Uh-oh, till I got to the second derivative, that gosh darn 2. So I plugged in 0, and I can see that all these terms are going to go away, right? Bye, because I'm plugging in 0. But this time I'm left with 2 times the second coefficient. Annoying. What happens when I do the third derivative? Oh, crap. Again, when I plug in 0, this term's going to go away and all the rest of the terms are going to go away. I am left with the third coefficient, but a freaking 6 in front of it. Ugh. All right, let me go back and make some notes here. So, taking away the derivatives in the original actual expression. Well, no, I guess I left the original up top. I did mostly get my coefficients, pretty much, right? The initial coefficient came from plugging in 0, right? And that is equal to the function at 0, right? Because the polynomial is equal to the function at the center. Now, my coefficient 1 is equal to the derivative at 0 over 1. And I don't have to put that over 1, do I? But I just did, because I wanted to. I can still say f that's also equal to f prime of 0, because remember, at the center, all the terms are equal at the center. All those first. What do I do here, though? Now again, remember, key understanding here is that I can only replace p prime of 0 with the original function at 0. Only at the center, right? Everything radiates out from the center. I couldn't do this for any other part. I could not replace the polynomial with the function except at the center. But all of a sudden, notice that I went from a 1 to not just a 2, but a 2. I'm yelling at you. Why would I yell? Look what happens here. Wait just a second, I think I see a pattern. Whoa, pull that out at parties. Totally impressive. Look at how I get each one of the coefficients. Each one of the coefficients, if you want the coefficient in front of the x to the 0, it's the function at the center, this is the center, over 0 factorial. If you want the coefficient of x to the first, it's the first derivative at the center. Notice first derivative goes with 1 factorial. Oh, by the by, what is 0 factorial? Yep, it's 1. If you want the coefficient in front of x squared, you have to divide by 2 factorial, and the numerator is the second derivative evaluated at the center, and so on and so forth. Coefficient in front of the x cubed, divide by 3 factorial, evaluate the third derivative at the center. So that's what this general term says. You want the coefficient in front of x to the n, you have to divide by n factorial, and you're plugging in the center to the nth derivative of f. Oof, that's a lot of work. This was developed by a man named Colin Maclaurin. He was a Scotsman, so I assume he's wearing a kilt there in that picture. But this is the Maclaurin power series, and that is any series centered at 0. Now, if you look very carefully, right, and I talked about this last week too, right, if I cover up all these terms, this is mx plus b. Slope comes from the derivative, x to the first plus the constant. These terms are the best quadratic fit, so on and so forth. So I can use Maclaurin to construct any power series centered at 0 with this pattern. So let's pretend I didn't recognize that this was a over 1 minus r. Because remember, you did this in the warm-up, and it was much simpler than using Maclaurin. I'd rather not use Maclaurin if I've got geometric. Please use it, but I'm just going to show you that I get the same thing. So I'm going to use Maclaurin because there's no shift. I got the power. So again, remember, we're pretending we didn't recognize the geometric series. Step 1, find the derivatives of the function you want to construct a power series for. So there's my function. There's the first derivative, the second derivative, the third derivative, and the fourth derivative. Step 2, evaluate the function and its derivatives at the center. That's key. Now for Maclaurin, what is the center always going to be? Yeah, 0. So here's what I'm going to do. My polynomial is my original function at 0 times 1, right? Remember, you're going to evaluate this as this is a 1. And divide by your factorials. So notice I separated out step 2 and step 3. Don't forget to divide each derivative by the appropriate factorial, because sometimes if I put that together, kids just do the derivatives, especially if the derivatives are a fraction, and then they forget to divide by the polynomial. So I got a 6, right? Do you buy what I'm selling there? When I plug in 0 to here, I get 6 divided by 0 factorial. I get a 6 there too, and I think you can see that without a problem, that I put 0 in there and I'm dividing by 1 factorial. But do you buy that I get a 6 there? Right? When I put 0 in up here, I evaluate the derivative at 0, and I get 12, don't I? 12 divided by 1 cubed. I actually get 12 first. F double prime at 0 is 12. But what am I dividing by? 2 factorial. How about the third derivative? Right, I'm putting in a 0 there. 36 over 1 minus 0 to the fourth is 36. So I'm getting 36 here. But what am I dividing by? That's not a 3, remember? It's a 6. And what is 36 divided by 6? Shocker! And then lastly, right? I'm putting the center here. 144 divided by 1 minus 0 to the fifth. The fourth derivative evaluated at 0 is 144, divided not by 4, but what? 4 times 3, 12 times 2, 24 times 1, 144 divided by 24. Guess what that is? You got it, 6. Now, that was much, much simpler to do by recognizing a over 1 minus r, right? And recognizing that I had a over 1 minus r meant that I could see that my interval of convergence was r, the absolute value of r needed to be less than 1, meaning that I would get a convergence series for any x between -1 and 1. That's like the price to pay for using Maclaurin, is that you don't see the interval of convergence right away. We have to let that go for a little while. It'll come back, but with a geometric series, I've got my interval of convergence right away, simply from the fact that I was using a geometric series. So again, a Maclaurin series is a power series generated with this formula using the derivatives evaluated at the center divided by the appropriate factorial. And there's my IOC, but remember, my IOC only happened because I knew that I had a geometric series. This is Brooke. Brooke-Taylor actually came before Maclaurin. Every Maclaurin series is a Taylor series, but every Taylor series is not a Maclaurin. Are you buying what I'm selling? It's kind of like the square rectangle argument, right? The Taylor series has any center, so it's the derivative at any center, and a Maclaurin series is only a series centered at 0, right? So here's the thing, when AP asks you to build a Maclaurin series, they don't have to tell you what the center is. You're supposed to know the center is 0. But if they say Taylor, they have to give you the center, even if they intend the center to be 0. So if I wanted you to make a series for 6 over 1 minus x, but with a at -2, you would have to replace every x with x minus -2. That would be annoying to do. And then I would have to use derivatives finding that and evaluate the derivatives not at 0 but at -2. Right, so there's the Taylor series formula. So for this particular problem, right, I would be evaluating the original at -2, and this would be x minus -2 to the 0. Right, I would have -2 everywhere, here, 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 here. But the basic formula of derivative over, right, first derivative evaluated at center over 1 factorial goes with x to the first. Second derivative over 2 factorial goes with x minus the center squared. Third derivative over 3 factorial goes with x minus the center cubed. Right? Fourth derivative, 4 factorial, x minus the center to the fourth. Whew. Oh, I forgot I did that. I could adjust my IOC too, right? My IOC would just shift. And hopefully you can see that -2 is in the center there between -3 and -1. Crazy whack funky, right? So there is a function that was geometric. We could have done a geometric, right? We could have done just like we did in the warm-up. But what about a function that is actually not geometric? Let's practice on that. Ooh, our old friend sine x. Can you make me a power series representation for sine x? So here's what I do. Step 1. Coefficient x to the first, coefficient x to the first. I'm sorry, 0 to the first, blah, blah, blah. Then I take derivatives. Well, fortunately, taking derivatives of sine ain't no big thing. Then I evaluate the derivatives at the center. Can you tell what the center is here? 0. So, oh, hold the phone. What is sine of 0? Whoa, sine of 0 is 0, isn't it? What is cosine of 0, right? I am now going to go to the first derivative, right? And I'm going to put in 0. Oh. So f prime of 0, right? First I did f of 0, which is sine of 0, which is where I got this 0 from. Now I'm going to do the first derivative at 0. What's the cosine of 0? Yeah. And then what are you going to divide, though, by? So that's 1. Oh, hey. The second derivative is also a sine. I don't even care that it's negative, because what is any sign, positive or negative, at 0? Well, gee whiz. I'm not going to see the x to the 0 or the x squared term. Oh, snap. Can you see what's happening here? Right? Negative cosine, right? I plug in 0 here. Plug in 0 here. Cosine of 0 is 1. Negatize it, and I get negative 1, but don't forget you're dividing by 3 factorial. And then the next term is going to be 0. Hey, can you see what's going to happen here? What's the pattern for all, as I keep going on? Which terms are going to drop out? Oh, all the even powers drop out, and all the what powers stay? So the power series representation for sine x looks like that. Without, and I wouldn't actually write the 0. Oh, snap, look, the signs alternate, right? So can you see the pattern? What are all the factorials going to be? Yeah. 1, 3, 5, 7, right? All yelling. And the signs are going to alternate. That's the power series representation for sine. Hey, what powers are left again? Odd ones, right? Hey, do you remember from pre-cal? What kind of function is sine? It's an odd function. Oh, snap. Math is cool. Mic drop. So here's my little table saying what I did. My original function was sine x. I did the first, second, third, and fourth derivative. And I evaluated the original and all the derivatives at 0. And then I divided by the appropriate factorial. And I got a sine as an odd function, which means all the odd powers are left. 6 over 1 minus x is not a series you want to memorize. Sine x is a series you want to memorize. So, in your calculator, if you get your calculator out, but make sure you're in radians. Make sure you're in radian mode. I want you to type in, I want you to use this polynomial, and I want you to evaluate sine of 0.1. So instead of x, I want you to put in 0.1. And I only want you to do it for these 3 terms. So you're going to enter 0.1, technically divided by 1, minus 0.1 cubed divided by 6, right, or 3 factorial, plus 0.1 to the 5th divided by 5 factorial, or 120. Then, as long as you're in radian mode, I want you to hit sine of 0.1. Pretty freaking close. And you know how you get closer? put more terms in there. Right? If you added this, what would the next term be? Well, the next term would be 0. What would the next non-0 term be? Right? It would be negative. This would be a negative. And you would have x to the 7th over 7 factorial. Now, don't forget when you're entering this negative, you have to enter negative 0.1 cubed over 6. Right? But I got 0.0915 with 3 freaking terms. I mean, that's just freaking nuts. How do you think your calculator is evaluating sine of x? It's programmed with the power series, that's how. And not that very many terms. Ugh. Math is cool. All right, so here's how AP likes to test you on making sure you know the formula without just memorizing the formula, right? So yes, you're going to have to build a function, but here, you know, you could just program, right? You could take your calculator in and pull up some program, or write on, you know, do something not honest and write it somewhere what the formula is for the power for a Taylor series or Maclaurin series. But look at how clever they are here. They're not telling you what the original function is, but they're telling you that this function does have derivatives that exist for all, you know, so the first, second, third, all the derivatives. You don't have any issues with differentiability. Then they're giving you the function at 3, the first derivative of the function, first derivative at the center 0, right? This is your center. They want the third order. So order, you need to know that vocabulary. Third order means you used the third derivative. Third order means you used the third derivative. It doesn't necessarily mean the third term. It means the third derivative. Okay, so write the third order Taylor. Okay, they said Taylor. So if they said Taylor, they have to give me a center, even though I kind of suspect what the center is. But if they say Taylor, they must give you the center. And then they ask me to use it. So here's what they want to see. So, and I remember I told you AP gets real picky here about using approximates and equals. So you want to say f of x is approximately the polynomial and sometimes this notation is used to indicate the third order polynomial. I'm going to make a mistake. Are you ready? That's not it. That's not it. But I've made 2 mistakes. Right? What did I do? I didn't have to find the derivative or evaluate the derivatives. They gave me the derivatives. And I put the derivatives with their appropriate x to the first, right? I put the first derivative with x to the first, and the second derivative with x squared, and the third derivative with x cubed. Who did I forget? You got it. I forgot the factorials. Technically, they all have a factorial. You do not have to simplify, right? But some of these do. If I wanted to write this a little bit simpler, especially since I'm going to have to use it to plug something in, I might want to write that the third degree polynomial is 3 minus 2x plus 4x squared plus what? This 3 is really a 6, right? So isn't this, so that's 4 over 3 times 2 times 1, and this is 2 times 2, right? So this 2 will cancel out with this 2, and I'm left with 2/3 x cubed. And then they're asking me, remember, to use the polynomial. So the third degree polynomial is exactly, shut up, Dylan, is exactly equal to 3 minus 2 times 0.2 and you have a calculator to do this, right? And you get some number which is approximately f, which I don't see, of 0.2, right? You get some number here, whatever you punch in your calculator. And what you need to know is that a function I don't see, so I can't check it. But because I have an approximator, a third order polynomial approximate of some unknown function f, I know that I'm pretty darn close to f of 0.2. Now, something that is key here is that the reason I use this approximator with confidence is that 0.2 is pretty darn close to what? The center. Right? It would be silly to use this function, I'm sorry, to use this approximator to approximate the function at 2.2, right? If I wanted to approximate 2.2, I would have to make my center 2. All right? So I don't know if you saw on the first screen that my the problems that I did for you, because they're in the homework solution file. If you wanted to practice them, I wouldn't start with number 1. I don't know why the textbook put number 1 as kind of a nastier one. I mean, it's the same process. It's just got ugly numbers with it and nasty derivatives. But not even nasty, just annoying derivatives. But go back and try that one. But some of the later ones are easier. Oh gosh, I forgot I did that too. Oh, look, I wrote it out. 2.765. All right, have fun, and hopefully I will be able to continue to give you some enrichment activities as we go along, and please don't worry. Please keep healthy and happy with your loved ones, and know that this stuff will all figure out for everybody across the country, but that my goal and my agenda is to make sure you have resources that you can optionally use to try to get ready for an AP exam, whenever that AP exam is, if you want, but it is not required and not expected when you walk in. If we walk in and see each other again this year, that I'm going to assess you or ask you what you watched or anything like that. This is purely just trying to do the right thing for you. Talk to you later. Bye.